Hi guys, it's your guy Olumde, and today we'll be solving another one of the most commonly asked tech interview question, N queens. It's a DSA problem that is commonly asked by top tech companies including Google, Amazon, Netflix, Microsoft, Metal, Apple, and other top tech companies. The problem statement states that there is a chessboard of size n by n, meaning that n rows and n columns. Your goal is to place n queens on the board such that no two queens attack each other. Return the number of distinct configurations where this is possible. We are giving these two examples here, right here. We are giving a single example, right? We are giving a single example, and where n equals to 4. So that's why we have 4 rows and 4 columns, and then we are asked to return the number of distinct configuration whereby we can sort and place the queens on n queens on the board such that this queen will not attack each other. So these are the n queens, which is also 4, since we have n rows and n column. So since this is 4, this is actually a 4 by 4 matrix, 4 rows and 4 column, and then we are actually asked to place n queens on the board such that these n queens are not going to attack each other. So if you look at this these two possible configurations, you will notice that in these two configurations, no two queens are gonna attack each other, right? And then why the answer and the output is 2 is because there's actually just 2 ways in which we are gonna place the queens on this board, on this n by n chessboard, such that no two queens are gonna consume or attack each other. Look at this place now. You know how queen attack each other is in this direction, right? So queen attack themselves in this direction of diagonally, horizontally and vertically. This is vertically, from the top to the bottom, that is vertically, right? So in the sense that for this particular queen, any other queen that is along this column can be attacked. So that is two queen must not be on this same column, right? So similarly, horizontally, 2 queen must not be on this same row. So these are the laws or rules for in placing queens, in a chess game, right? So, and also diagonally in the sense that this diagonal down here, no two queen must be found. If a queen is actually let's place a queen right here now, there will be a problem because this one is gonna attack this one. So no two queen must be placed like that. So both diagonally and anti-diagonally. Anti-diagonally means that the other way around. So it's just a situation like this. Anti-diagonally is a situation like this, right? So these two queens, even though they are anti-diagonal in nature, they are gonna consume each other. So it must not be like that. So both in this direction, in this slant direction, like this, right, is gonna consume each other, and also in this other direction like this, they're gonna consume each other. So, and if you look at this structure that's given here, you will see there's no way in which there exists 2 queens in the same diagonal or anti-diagonal or horizontal or vertical position, right? So, and there are 2 different ways in which you can place the queen or queens, n queens on the board, on the n by n board. There are just 2 different ways you can place it such that they won't consume each other, and that's why we have this output here as 2. So that's what this problem statement is trying to tell us. We should return the number of this distinct configuration whereby it is possible. So we're not just trying to find out if it is possible to place n queens there, we just want to find out the number. After finding a distinct way, we try to backtrack to find other similar ways whereby maybe there are other similar way whereby we can place the queens on the board. So you see this one here, first queen is placed there, but here in the other arrangement it is placed there. But one thing that's common to both of them is that they won't attack each other, right? So let's dive into the problem, into solving the problem. So this is just a simple rule for the queen, for placing the queen, whereby no other queen occupy the same row of that square, right? So of that board. So no two queen must occupy the same row, and no other queen or no two queen must occupy the same column, and likewise no other queen or no two queen or two or more queen must occupy either diagonal of that square. You know, diagonal is divided into two. We have the diagonal and the anti-diagonal. So right, diagonal is this one that is pointing this direction, slant like this, while anti-diagonal is this other one that is slant like this. So, and what we are trying to say is that this is one diagonal, this is a diagonal like this, these three, you understand? But when we talk about anti-diagonal, we are talking about something that comes in opposite direction. So instead of coming like this from here to here, it comes in this opposite direction, moving toward, is slanting toward the right, just like right slash and backslash. So now that we understand the rule of the game, let's look at how we can actually place the queens on the board. A straightforward way to place the queen on the board is actually to place each queen on the board one by one. So we place the first queen on the board, right? Then we place the second queen, then we proceed to place the third queen, and whenever we come across, whenever we are placing a queen, we make sure that each queen is placed on a safe square, that is on a square where it's not gonna be attacked by an opposing queen, right? So but in a situation by a previous queen, you understand? And whenever we come across a situation whereby a queen, there's no way you can actually place a queen without it getting attacked by one or more of the previous queen, then we can actually backtrack to the previous queen to that queen, so that we can reposition that previous queen and then try again to try to check if this new queen can now be placed safely on the board. And what I'm trying to say is, let's consider this scenario now, whereby we place the first queen here, right? So well, before we consider this scenario, a more efficient way, or let me buttress what I said the other time. So more efficiently, we can actually place each queen on a new row, so that we don't need to look for conflicting queen in the row, right? Meaning that when we want to place the first queen, we situate it, since we have n queen, right? And we have an n by n matrix, so you can always place each queen on a new row, right? So by placing each queen on the new row, we don't need to check for conflicting rows or conflicting queen on the same row. Why? Because we actually intentionally and explicitly are setting each of these queen on a new row. So we just have to check for conflicting or opposing queen on the same column, on the same diagonal or anti-diagonal, right? Fine. So let's consider this particular example here. We place this queen here on the first row, right? And then we try to place this second queen here. Fine. You see that they are not conflicting. Why? Because since it is not actually in the same column, not in the same row, of course, and not in the same diagonal. This is the diagonal for this particular one, so the diagonal actually different, right? So fine, it means that they do not conflict, so they can stay there without attacking each other. So but when we want to place the third queen, right, so we're gonna be placing it on a new row as well. So but you will see that on placing it on this first row here, it's gonna be attacked by this by this queen up here, right? Because it is in the same column. If we place it on the second row, it's gonna be attacked by this particular queen here, because it is in the same anti-diagonal, right? So it can attack it. If we place it on this third row, it's gonna be attacked by this same queen, because it is actually in the same column. And if we place it on this fourth row, it's gonna be attacked also, because it is on the same diagonal. Right here the same anti-diagonal, but right here the same diagonal, right? So because of that, there's no way we can place this queen on this particular row without getting it attacked. So what we do is that we backtrack to the previous queen to reposition it, so that we might be able to position this new queen very well, right, on the board. So now backtracking, now we try to look here. You see that we cannot position this particular queen. We can't position it on the first row because it's gonna be consumed by this queen up here, which is the previous queen to this previous one, right? We can't place it here as well. Why? Because it's gonna be consumed likewise. We can't place it. Okay, this is where it is. I am initially, right? This third row, this way, if you see it here, that is where it is, right? So we now shifted it to the rightmost one, and by shifting it to the rightmost one, when we now go back and try again, try placing this third queen again, we can easily place it on this second second row, second column, right? We can't place it on the first column. Why? Because it's gonna get attacked by the very first queen in the board. We can't, but we can place it on the second one, because right now we have actually shifted the previous queen, and then queen can be placed here. Here is a visual representation of how we traverse the board, actually, right from how we traverse the board, right, and how we place the queen on each row of the board. So don't forget that the problem statement asks us to actually find and return the number of distinct configuration that is possible to place the queens on the board, whereby no two queen is gonna attack each other. What this is simply trying to tell us is that we want to find all possible distinct ways of placing the queens in the board without any two queen conflicting or attacking each other. And because of that, you should understand that that simply means that we actually are not just interested in getting just one method. We want to explore all possible methods to get all possible distinct configuration of arranging the queen in the board. And because of that, we are going to start with an empty board, right, whereby we will place the queen on the board one by one. Now this is what it looks like if we place the queen on the very first square of the board, or let me say on the very first cell of the board. This is it. So this is what it look like when we put it on the second, on the fourth, on the third, and on the fourth. And we'll be doing this, we'll be exploring all. Why? Because we just want to check if any one of them, or if more than one of them, is going to lead to a valid placement or a valid structure whereby no two queens oppose each other. So, and we just want to keep incrementing anytime we can find a configuration that is valid and does not oppose each other. So we want to explore the whole cells and squares in the board, in the chessboard, right? So, but for the sake of the screen is not so large enough, so we are just going to be considering one part, right? So which is the part of placing. Who knows? Actually, the answer is 2, right? The answer to the problem is 2, meaning that there's definitely going to be more than one part that leads to an answer, right? So, but we are just going to be considering a single part here. So, and then we when we can find one part, then we know how to find multiple parts, right? By just trying for other possible configurations. So, considering this part here now, we place the first queen on the third square, right? So now, because of that, we try to figure out any more how to place the second and the rest of the queen, right? So we can either place the second queen, fine, we are always gonna place the second queen on the second row, right? So we can now place it on the first cell of the second row, or the second cell of the second row, or the third or fourth. So looking at it now, you see that only the first cell is valid. Why? Because by placing the first queen on the third row, if we place the second queen on the second row, they are gonna attack each other. Why? Because it is the anti-diagonal. Similarly, if we place it on the third row, which is on the column, I actually mean column, you understand? So if we place it on the second column, it's gonna attack each other. If we place it on the third column, which appears to be the same column as the previous queen, they are definitely going to attack each other. Even if we place it on the fourth column, which is the last column in this case of 4, n by n matrix, n by n chessboard, right, which is 4, n is 4 in this case. So if we place it here, it's still gonna attack each other. Why? Because they are diagonal to each other. But if we place it on the very first, if we place the second queen on the first column of the second row, they are not going to attack each other. So let's follow that now. Since so far it is valid, let's try and check if it can contain the third row without while being valid as well, right? So because there's no case whereby these other 3 cases is gonna be valid. Why? Because even by placing the second queen, it is not valid. So even if you proceed to put in the third and the fourth, it's still not gonna be valid. So let's consider this one and put in the third queen now. So putting the third queen on the very first column of the third row is gonna render it invalid, because there's a queen in that same row. Similarly, putting it here, you know, you will understand by looking at, you see that this is diagonal, right? So it won't work. If we put it here, because it aligns with the column of the first queen, it's still gonna attack each other. And similarly, by putting it here, is not going to attack each other. Why? Because it is not diagonal. There's not any queen in that diagonal or anti-diagonal or in that column. So let's proceed and place the fourth queen now. So if you can place this fourth queen successfully in one of the columns in the fourth row, definitely we found one distinct configuration whereby you can place the chess without the queens in the chess without attacking each other. So if you look at it here now, oh sorry, right here I did not finish this. Let me finish it up now. So right here I placed the fourth queen on each and every row. So you see I placed it on the the fourth queen on each and every column of the last row or fourth row. So I placed it on the first column, second column, fourth column. I try all possible configuration, and you will see that only this second one actually got it right, while the remaining one are wrong. So why? Because this second one is not going to be attacked by any other queen in the board, and because we have been able to successfully get to the last queen and it is not attacked, definitely the previous one to that last one have not been attacked for us to get to the last one. Don't forget that when we get when they become attacked at each of these points here, that you see that this orange color we stop. So why? Because there's no need to go further after it is attacked. So for us to get to the very last queen, the very last queen in the very last row, so and then to be able to place it, for us to be able to place it successfully, definitely all the queens have been checked, they have been placed successfully. So and you can see them here. The first does not conflict with anything, second also does not, and third and fourth. So we have found one correct configuration. So and then what we want to do is just try other means. So we still have this to try, we still have this second one, this first one to explore. So that's how we solve this problem, by exploring each possible one. If it actually cannot work out, we move on to the next. If it can, we explore deeper and deeper, just like this. And then when we find one, we just keep on exploring until we get to the very last one here, and we explore this very last one and make sure that we have find every possible configuration, and that's when we stop, and that's where we output the code in the results. Now one challenge in solving this problem is, how do we detect opposing queens? How do we know that, okay, this queen, this particular queen here is gonna be attacked by this particular queen with similar column up here? So how do we detect it? Fine. One way is that whenever we want to place a queen on a square or on a cell, right, we can try to check through the rows, the columns, the diagonals, to see if there is any other queen in that particular row or column or diagonal. So we know quite well that if there is a queen, that queen is going to attack it, right? But that is quite inefficient, because we are actually going to be checking that for each and every queen that each and every time we're even trying to place it. We're going to do that for each and every queen each and every time. So and that's a lot of time, a lot of inefficiency. So but one efficient way to do this is that if we consider and observe well, we will see that we are not really interested in the position of these queens. We just want to know, we don't really want to know, okay, how many queens are on the same row or column. We just want to know if there is a queen on that row, or there's a queen on that column, or there's a queen on that diagonal, because we know that if there is, it's going to attack irrespective of the number. Even if it's just one, it's going to attack the queen. So because of that, you can use a hash set to keep track of the queens. So whenever we place a queen on a particular square, you know, it's a particular square, we have a coordinate row and column coordinate, right? So sorry, a particular square is going to have a row and column coordinate. So whenever we want to add a queen to a cell, right, we are going to keep that row in a hash set. I mean the row that that queen belongs to. Fine, we want to add a queen to the very first row and very first column, so we add it to the hash set, so that we add the row coordinates to the hash set and the column coordinates to another column hash set. And why we are doing this is because, don't forget, whenever we want to try to check if a square is gonna if a queen is gonna be attacked, we don't necessarily need to check both row and column. If it is either in the same row or the same column or the same diagonal, either of these things is gonna be attacked. So that's why we have to keep them differently. So all it takes is just to be in one of these coordinate, or let me say one of these row and column and or diagonals, right? So because of that, for each square we are gonna be placing on the board, we are gonna record the row and column and diagonal in a different hash set. So we are going to be having the row diagonal, the column diagonal, the row hash set, the column hash set, the diagonal hash set, and the anti-diagonal hash set. But one thing I want to do is that we don't need, for efficiency, we don't need to keep track of the row hash set. Why? Because we have decided to place each row on a new, each queen on a new row. So we don't need to keep track of the trouble with the fact that, oh, can there be any more row, any more queen on that same row? No, they can't. We are always placing each queen on a new row, right? So because of that, that one is solved. We don't need to consider the row, but now we are going to consider the column. So for each queen we are placing, keep track of the queen in the column, right? So keep track of the queen position, the column coordinates on the column hash set, so that anytime I try to place another queen, we can look up for that that square that we are trying to place the new queen. We're going to try to check if the column hash set does not have that same, if there's not a queen in that same column, a previously placed queen on that same column, because if there is, we would have added it to the hash set, to the column hash set particularly, and we could figure out that, oh, it's gonna be attacked, we can't place it there. So similarly now, don't forget, just like we did for the column, we want to do for the diagonal. Why? Because if two queens are on the same diagonal, they're gonna be attacked. So and one thing we wanna do, one thing we observe mathematically is that each a diagonal actually have the same ID of r minus c. Okay, don't forget this is a diagonal now, just like you can see here. This is a diagonal, this is another, this is another, this is another, this another, and you see that they have the same number. So what it means is that you can identify the same diagonal by we have the same ID of r minus c, meaning that look at this now. For this particular, let me shift this down a little. For this particular cell right here, you will see that the value is 0 all down throughout this diagonal. And how we can do that, how we can identify that, is by doing their r minus c. For this particular cell, the row is 0 and the column is 0, right? So 0 minus 0 gives us 0. So similarly for this one right here, that I actually appear visually, just like you can see it, they're on the same diagonal, but how we can identify it is that what they will both have the same r minus c ID. So you see that this is 1 minus 1, which gives us what? 0. So similarly this will be 2 minus 2, and this will be 3 minus 3, right? So that's how we got that, and that's how you can identify diagonal equal this squares of the same diagonal. Similarly look at this. This is 2, because the r minus c for this is 2 minus 0. Similarly another cell or another square of the same diagonal will be 2, because this is 3 minus 1. So that's how it goes on and on. So you see now that anytime we can identify the diagonal or queens that are on the same diagonal by performing r minus c. That particular queen coordinate, just try to do r minus c. If it is in the diagonal r set, definitely there is a particular queen in that diagonal and it's gonna attack it, right? So similarly we can do the same for anti-diagonal. Why? Because queen is gonna queen go all way, just like you can see here, it goes diagonally and anti-diagonally in all 4 directions, even more than 4. So okay, up, down, left and right. even diagonally. So it's more than 4. So and because of that, we actually can do the same thing for diagonal and anti-diagonal by doing r plus c. So anti-diagonal is similar to diagonal, but it is in the opposite direction, in opposite slant direction. So if you look at this, this is a 1 plus 0, right? So and that is why this is a 1 plus 0, and that is 1, right? So you see that right here we have 1, and right here we have 1. Why? Because here too is a 0 plus 1, here is a 1 plus 1 plus 0. And what I mean is that look at this particular cell. You look at this particular cell, you will see that it has a row of 1 and a column of 0, right? And 1 plus 0 gives us 1. Similarly, the same a cell in the same diagonal or in the same anti-diagonal have its row to be 0 and its column to be 1, and 0 plus 1 gives us 1. So every cell in the same anti-diagonal, we have the same idea of r plus c, right? They will have the same idea of r plus c. So similarly, it goes on like that. Look at this one that is 5 here now. You will see that it has a row of 3 and a column of 2, that gives it 5. And similarly, another square in the same anti-diagonal have a 3 and 2 here, which is 5 as well. So by just adding them up, adding the r plus c up and adding it to the r set, or looking it up in the r set, in the anti-diagonal r set, we can easily find if there is an existing square, an existing queen in that particular diagonal, and if there is, we cannot place the queen there. So this is how we detect opposing queen in each column, diagonal and anti-diagonal. Don't forget that we left rows because we have decided to place each queen on a new row. So now, how do we now place queen and remove a queen? So we've talked about how to detect a queen. Then how do we place and remove it? Why? Because whenever we detect that a queen is already exists in that row, in that column, diagonal or anti-diagonal, what we want to do is that we want to backtrack to that previous queen, to the previous queen, so as to reposition it. Whenever we reposition it, then we try again, so to try to check if the current queen can now be placed without being attacked. So just like this, consider this scenario now whereby we find out that okay, I'm just trying to consider this scenario whereby we find out that okay, on placing this fourth queen here is gonna be attacked by this one on top here. So we backtrack to this one on top to reposition it somewhere else, and if by repositioning it somewhere else, it's actually we are able to place it on a square that does not got attacked by another square, then we can now try again to place this new square or somewhere else. So if we try all this combination and none of them will, definitely there's no way we can achieve a configuration from that part, so we just backtrack to the other part. So that's what that's how we'll be placing and removing a queen, and we can do that in terms of code by just removing it from the row set. Sorry, we talked about removing the row set. We are not using it because we are placing each queen on a new set on a new row, so we don't need to keep track of the rows. Fine, we are going to be removing a queen by removing its column coordinate from the column set and from the diagonal and anti-diagonal set, so that we have efficiently removed a queen, right? So all we are just trying to do when we detect an opposing queen, we try to remove a queen, right? We try to remove the previous queen so that it won't attack it, and we do that by just what I just discussed now, by placing and removing a queen, by removing them from the art set. So well, it might look somehow, but I believe you're gonna understand as soon as we go into the code implementation now. Let's go into the code implementation for n queens DSA problem. So we'll be having our function as n queens, n queens. So it's gonna be taking in n, right, which is actually the n by n board, is the integer n that will form the n by n board, two-dimensional board, right? So okay, let's pass the function for now, and let's place these things. N equals to 4, right? So from the problem statement, we see that n equals to 4, and we are trying to print. I wanna call the function print queens of n. Alright, so this how the function definition function call is gonna be, and this is gonna look like. And don't forget, what we want to do is that we want to traverse the board, just like I show you in the logic, right? So and we are gonna be calling this DFS that will help us to traverse the board. So we are gonna be passing in the first row, which is actually row 0, right? The first row is always row 0. So because we are gonna traverse the first row first to place the first queen on the first row, then we can traverse the second row and up to the nth row to place the nth queen. So okay, I'm passing in sets, and what this set is there is stand for is actually the column sets, then the diagonal sets, then the anti-diagonal sets, right? So that's what is there for. So don't forget, this set is where we are gonna be inputting every we are gonna be storing the position of each queen that we placed on the board, right? So that we can keep track of this queen and know if it's gonna attack any future queen, so, or if it's gonna be getting attacked. So okay, now we are gonna be defining in a global variable, so res, which is the result, so it's gonna be 0. So don't forget that we want to return the number of distinct configuration whereby we can arrange queens on the board without getting any of them attacked. So this res is gonna be helping us to keep track of this the number. So right now we have 0 at first. Why? Because we don't even know if at all any of these queens are not gonna be attacked after placing them. So but as we traverse through the board, anytime we are able to place the nth the O4 or nth queen on the board, all of them, without getting any two of them attacked, we can increment the result by 1, meaning that we found one possible configuration. So that's what we are doing here. So that's why we are defining this res variable to help us to keep track of it. So, and then at the end of the day, we'll be returning res. So hoping that after navigating through all the O chessboard, we are gonna be able to determine the total possible configuration. So now let's define the ref, and let's define the DFS function, which is going to help us with that, with traversing the board. So we have the row, which is an integer, then we have the column set, which is actually an hash set. Similarly, we have the diagonal set, which is also an hash set, right? And we have the anti-diagonal, just like I explained in the logic. So anti-diagonal is going to help us to keep track of any row in the same anti-diagonal. Similarly, diagonal is going to help us to keep track of any row in the same diagonal. So we are having this returning none. Why? Because all it does want to do is to traverse through all possible cells and squares in the board. So along the way, we'll be keeping track of the result. And now we are going to do that is by checking that if r is equals to n. Okay, I forgot to send in n. Let's send in n. So where n is actually the number of queens and the number of rows and columns, right? So n is a n by n board. So if r equals to n, they want to increment our res by 1, and similarly we want to return. So and what this actually means is that in a situation whereby we are sending a row of 0, and we are going to be placing each queen on each row. So when we place the first queen on the first row, and second on the second row, and third on the third, and fourth on the fourth row, and it now gets to a point whereby row become equals to n. Don't forget that row is 0 based, right? So if we are dealing with 4, it means 0 1 2 3. So in a situation whereby row now exits 3 and becomes 4, definitely it has actually traversed all the rows in the board. It has placed each and every one of the queen on each of these rows, starting from row 0, row 1, row 2, row 3. So in a situation whereby row now become equals to n, definitely it means that we have been able to place is a queen on each of these rows up to the last row. So because of that, we are gonna increase our res by 1 and then return, because we don't want at that point it has gotten to the leaf node, or let me say the last possible sorting, or last possible traversing. You know, we can't traverse outside the board, so it has gotten to the last bus stop. Okay, but in a situation whereby it is not like that, we that means that the if condition is not going to be executed. So, and what we are just going to do is that for that particular row, so it has not gotten outside of the bus, it has not exhausted the all rows and columns, the all cells of the board, probably is in row 0 or row 1 or row 3 or row 2. It has not gotten to the row 4. Because of that, we are just gonna iterate through the column in the board for that particular row, right? So that's what I did there for C in range of n. You might be like, why for C in range of, you know, this is a n by n board, so it has the same row and the same column. So I'm trying to traverse through the column now, so through each of the column in that board for that particular row that we are. So, and what we're gonna do is that we want to first of all check if C is in column sets. So meaning that I want to check if there is an opposing queen in the column set, or R plus C in okay, let's make it R minus C first, because R minus C represent diagonal set, right? Diagonal sets. Okay, let's call this diagonal set, please, for a more readable format. So if R of C in diagonal sets, or if R plus C in anti-diagonal set, just like I explained in the logic. So R plus C, R minus C, it represents it's an ID for all diagonals in that particular square, or in that particular board. You understand? So if any of them, definitely if any of them evaluate true, then there is going to be an attack on the current queen, right? So because of that, we are not going to place the current queen, we are just going to continue to the next column, hoping that probably in the next column there will not be a problem, there won't be an attack on the queen. So, and then if there is not, we just want to actually add, first of all we want to add it so that we can know that, okay, this place has been occupied by a queen. So column set dot add, we're gonna add this particular column. We don't need to add the queen or anything, we just want to add that, okay, this particular column now have a queen in it. Okay, so similarly we want to add the diagonal set dot add. Here we're gonna be adding R minus C, right? And similarly anti-diagonal set dot add R plus C, right? So, and doing that now, what we want to do is that, okay, we want to call DFS again on the next row, right? We have been able to place a queen on that particular row, so we want to call it on the next row. That's why I'm doing R plus 1, no more R, dot R plus 1. So if the next row appear to be the last, it appear to be the row after the last row. The row after the last row, we have the same value as n, right? Because rows start from 0. So if it's going to 3, it's gonna be 0 1 2. If it's going to 4, it's gonna be 0 1 2 3. So if it now gets to a point whereby the row is equals to 4, maybe we call DFS on a row that is 3 already, and we're adding 1 to it, definitely it's going to be 4, and it's actually specified that it has gotten to the end of the cell of the board. So it's just gonna do this and return. It's gonna increment our res and return. So sorry, but lest I forget, let me declare the res global, global global res. Why we are doing this is just meant to be like that in Python. You have to globalize that variable, right? Okay, doing this now, after doing this, we are still gonna call remove all these things from the column set, from this and from the diagonal sets. And why we are doing this is that, imagine a situation whereby that particular, just like I explained the logic, a situation whereby that particular queen does not fit in any of that cell, meaning that any of the cell or any of that square or that cell in that particular row, meaning that any of the column in that particular row does not fit the queen, is gonna be attacked one way or the other. So we have to backtrack to the previous row, to the previous queen, and to change to replace and to change where it is. I mean to reposition the previous queen. So because of that, to be able to do that successfully, we have to backtrack as if we have not placed the previous queen. So we have to remove it from the O point, R minus C. So remove it from the column, from the diagonal, from the anti-diagonal dot remove. So here we are going to be having R plus C. So we remove it from everywhere. So we clean the whole traces, and that way that's what we call backtracking. So this is how we solve this problem. So it's just gonna go on like that, and find all possible combinations. Don't forget that I'm doing for C in range of n, meaning that for each of the row, whether it leads to a good configuration, whether it increase our rest by 1 or not, it's still going to consider all possible rows. So that way we are going to be expecting that our rest is going to sum up to all possible configuration ever. So let's run this code and see how it goes. Okay. Oh, I know I said the other time that we're gonna be adding n to our DFS, but I actually did not add it in this function definition. So n is actually an integer, so we are using it to keep track of whether r is equals to n. So we need it. So and I just added it now to this function definition here. So let's run the code again and see. Okay, I think there's another error here whereby we do not add it. So we have to add it, column set, sorry, we not add the diagonal set in fact. So and the anti-diagonal set and the n, right? So what I think, because I'm quite in a hurry, because we've actually used a lot of time explaining in the logic section. So in the logic section, okay, now we have 2 returned, right? So this is 2 here, and because of that it shows that this is correct. So I really hope you understand this, and if you do, click on the subscribe button, please do that, please. Thank you guys.